I like being nice too. I don't.
That's good. Be nice. Don't be mean.
Yeah.
Be nice. It's a good thing.
Calculus chapter 2.
Okay, moving right along. Chapter 2. The derivative and the tangent problem. So differentiation. So now we get to put our limits to work. Yay. We've talked about the tangent line problem, and that's and we've actually done this essentially. Pre-calc. We already did this concept in pre-calc. We are going to give the definition of a tangent line with slope m, and in terms of the limit process. So we talked about, let me see here, they're going to use, I'll use what they use for their notation, which we've talked about as well. So in this, if we have the graph, whatever the graph is, and we have a point right here, we are going to take another point. If I want to know what is the slope along the curve right at that point, you can't have the slope at a point. Because if you have a one point, what's the slope at the point? It's unknown, or there's an infinite amount of possibilities. So it doesn't work. But if you have,
It's like, say if we sign like an x value, say if we say assign that ex value 3, you do the slope formula when you plug in x2 and x equals 4. So like, say if that's 3.
Okay.
And we could, if we find out the y and x at x equals 2 and x equals 4, we can use the slope.
Oh, the average in between?
Yeah.
Yeah, that is one possibility. The issue is that if your curve is really gradual at 2, then really steep, and then something like that, and you want to know the slope there. But like if this was 2 and then this was 3 out here, that slope like wouldn't necessarily match like there. So it's an idea, but even easier. Well, I don't know about easier, but the accurate way to do this is to find. We have to find the slope between 2 points, and so if this is our point, they will describe this as at C right there. So if you're at C, and then you're going to take this other point. I've discussed this before as the tangent line problem. You're going to take the other point, and you're going to move this other point down like this. You're going to move it in that direction so that you can find the slope between 2 points. So technically, you're finding what you would describe as a secant, right? The slope between 2 points, the secant. So that would be a secant. But as I move this point infinitely close, essentially it becomes a tangent. Now, this point right here, this is some sort of function f of x. And then in that, then my point is over C. Right here, this is over C up f of C, whatever your function is. Then this other point out here that we would have, okay, that's over C plus an additional amount. So to get to this point right here, you could assign another variable like Z or something like that, but they don't. They say it's over C, so you have to come over C plus a delta x, a change in x. So the distance right here between these two is delta x, a change in x. And so this coordinate point up here would be over C plus delta x, comma, f of C plus delta x. And so the notation can get a little cumbersome and confusing, but hopefully we can understand what they're referring to. And so the slope of the secant would simply be right between the 2 points. You would say y2 the minus y1, so y2 minus y1 over x2 minus x1. And when you reduce that or simplify, at least in the bottom, we just end up with f of c plus delta x minus f of c all over delta x. And then we think about what slope is just the change in y over your change in x. And sure enough, on the bottom, you get just the change in x is all that you have left. Now, with that, that would be the slope for the secant, but we don't want the secant. Ultimately, we want the tangent. But this formula sets us up for the tangent. The tangent would be the slope at one point, but we know we have to have technically 2 points to consider to find the slope. So what we do is we take this point right here. We've discussed this a few times, last year and this year, at the beginning of chapter 1. But we'll take this point right here, and we're going to move it closer and closer and closer to that point. In fact, we're going to move it infinitely close. And the way to move this infinitely close to this direction, what happens to delta x? As this point goes here, delta x is getting smaller and smaller and smaller. Therefore, we say delta x is going towards 0. And so the slope, if you will, of the tangent line, okay, or the slope at C, in this case, the slope of the tangent, is going to be equal to the limit as delta x approaches 0 of the same thing that we've just been putting, c plus delta x minus f of c all over just delta x like that, okay? So that is what they call, they say the definition of tangent line with slope m is going to be that right there. So what this is, they don't actually say m subtangent, but the definition says the slope of the tangent line. The other thing that they do throw in there, which we know, is they also throw this in. The limit as delta x goes to 0 of delta y over delta x. Just emphasizing that this is the slope equation, change in y over change in x. This up here would represent my change in y. That right there is the change in x as can be seen. Now in the pre-calculus book we discussed, they don't actually use the notation delta x, they use the letter h, just which is less notation, just two different ways to look about it. You can do either one, it doesn't matter. Delta x does help us recognize that we're talking about a change in x for that. Okay, the derivative of a function, the definition is, you have now arrived at a crucial point in the study of calculus. The limit used to define the slope of a tangent line is also used to define one of the two fundamental operations of calculus, differentiation.
Wow.
So, the derivative is simply referring to derivative, and we've used this word before, pre-calculus, we talked about it. The derivative is referring to the slope at any given point along a curve, or a line if you wanted to. There's no real need for calculus for that. So the derivative is just referring to the slope, like visually, the slope along the line or along a curve at any given point. So when we talk about that, when we hear the word derivative, think slope.
That's just what we were doing with the paint can, right?
Yeah, you're doing that, right? You're finding the derivative there, essentially, with the paint can dropping, which is the slope of it. But now you'll be able to do like an instantaneous flow, which it was. It was an instantaneous velocity as the time is approaching 2. So the derivative, just think slope. Oh, what's the derivative? Oh, what is the slope? So our notation is this, is if I want to refer to the derivative of a function, so if our function is f of x, the notation for this, for the derivative, is going to be, maybe this is the best way, but if I have f of x, the derivative notation is f, not to the first power, but it's called f prime of x, f prime, or the derivative of f of x. So this is the derivative of f of x. F of x is just my function, the notation is f prime of x. Now there's other notations that actually go with that, and those other notations, depending on what you're emphasizing, it could be dy dx, which would actually make sense, the delta y over delta x. It could be also written as d dx of y, okay, so the derivative of y with respect to x. Those are notations that we'll talk about and use. And you could also have a notation d dx of f, referring to it as in function notation. If it was y, it would be thinking of it as like a y equals. Those are all representing the same thing, f prime of x, dy dx, d dx of y, d dx of f. It just means the derivative of a function. So notation-wise, just think they all represent the exact same thing. And what that exact same thing is that if I say, hey, what's f prime of x, you're saying, what is the derivative? Again, I'm saying this as f prime of x, because that's the verbiage.
F to the first.
So, yeah, f to the first of x. F prime of x is equal to this right here. You're just finding the derivative, which is the slope. So I'm going to rewrite the exact same thing that we have up there. It's the limit as f of c plus delta x.
We're just thinking of different ways to make this complicated.
No. It's a way to describe it all.
If f of prime is the same thing as slope.
But
M of
c, now,
tangent is slope.
I actually do need to change something here. Is that this c would be at a specific point, like we were discussing over here. This was at a specific point c right there. The derivative, like f prime of x, since it's just x, it's the general, just change c to x, the general anywhere along that curve. Okay? So anywhere along that curve. That is your derivative.
Complicated.
Okay? So, the other notation I didn't put on there that you could see, you might see is like y prime. You'll see this, y prime. Is another one. You might see, I don't see this one very often, like d sub x bracket y, the derivative of y with respect to x. Now, if you were to change, let's say you have this, if you want to write it, you can, but let's say you have a function s of t is equal to whatever t squared plus 4. You have some function. If you were to do the derivative of this, easy, you just say s prime of t. But then what that changes is it changes these things as well. You're no longer doing it with respect to x, because the variable has now changed to t. You're no longer doing it, if you will, it's no longer y. You can think of this as like s equals t squared plus 4. So it'd be like s prime or ds dt. You just change the variables. Same thing as applying, just changing variables. So you're like, okay, what's the derivative of my change in s over my change in t? So we can make a note of that as well. Okay, now let's go ahead and look at, well, there's some other things like the alternate form, alternative limit form of the derivative. That is if you want to find let me write this, the alternative limit form of the derivative is if you're finding it at a specific point. So f prime of c in this case, that would be equal to the limit as x approaches c. So not delta x, but then it's going to be f of x minus f of c all over x minus c. And we'll should do a problem that.
Why is it not?
Why is it so complicated?
Why is it not what?
Like, why is it not limit as x approaches change in c?
Oh, the change in z? Well, this is just like
Oh,
referring to, this
that's
would be
specific.
like, if you have some sort of curve there, right? And if you're looking at what's the, derivative, meaning what's the slope there, then this would be c, and then you're just stating your other point is over like x. So it kind of eliminates the notation of delta x, and you're saying, okay, as x is approaching whatever c is, and so then your f of, this would be over x up f of x, and then this would be over c up f of c. So it's actually just a simplified form of that. So let's do a couple little problems. Interesting. There are areas where I guess I can mention where your derivative doesn't exist. What? And that would be, if you think about this, you have, let's say you have a greatest integer function, right? Like that, right? So here, if I said, well, what's the derivative, and we can look at this, what's the derivative at this spot, like right there in the middle? Zero, right? Meaning, what's the slope, right? When I say derivative, we said think slope, so what's the slope? You say, okay, it's zero. So then you say, well, what is the derivative? If I pointed here, you'd say, well, it's open circle, so there's no derivative there. But then you say, well, what's the derivative right here? Well, at the end point there, does the end point actually have a derivative? And in that case, the answer would be no, because, at the very end, you could change it at that point. The slope could be anything at the very end point. So in other words, your limits, if you remember doing limits have to apply from both sides for this. Now, another area where your differentiability creates an issue. So if you have discontinuity, it creates an issue. Another area where it's going to create an issue is if you come down here like this and then go back up like this. So it's not a parabola, it's a sharp corner. Like you would maybe say the slope, just looking at this, is a -1, and then the slope is equal to a +1. And then let's say this is over 2. So if I say, well, what's the slope anywhere along this side? The slope is -1. We can see that. Anywhere along this side, the slope is 1. But what is the slope right when it hits the bottom? And you say, well, the slope would be 0, except at a sharp corner, so not a parabola that comes down and curves back up where it gradually goes to 0. Yeah, there it's like teeter-tottering. It's unknown. So there is no derivative at the sharp corner.
It's not
The derivative does not exist. Okay, and the reason for that is the limit doesn't exist at that point. Because the right side limit, if you will, the right side derivative is 0, the left side derivative is 0. And so the limit may exist, so the limit exists, but it doesn't have a derivative at that corner. Also, graphs with a vertical tangent does not apply either, okay? So yeah, I guess with this one, the limit exists, like I stated, right? Because it does, as it goes, it's going to 0. Here, the limit is going towards 0. They're both going to 0, but the derivative on the left would be going to -1. The derivative on the right is going to 1, and it doesn't match. So the derivatives have to match. Whereas if you have a nice gradual curve on a parabola, you would say, yeah, the derivative here is a really steep negative, -10, -5, -2, -0.5. It's going towards 0, and here it'd be 10, 5, 2, 1/2, and it's going towards, the derivative is going towards 0, the derivative is going towards 0, therefore the derivative is 0. Here, -1, -1, -1, stop, 1, 1, 1, 1, 1, stop, there, it doesn't go towards 0. Okay, so it does not exist. The other times is you may have some sort of vertical tangent like that. We don't see that too often, but a vertical tangent, can you have the slope on a vertical line? No, so if you have a vertical tangent, a graph of a vertical tangent, then the slope would not exist there either. Okay, there is a theorem that we'll make a note of. This is the last thing before we look at a couple problems before our time is up. And that's theorem 2.1, and it just says differentiability implies continuity. So you don't have to memorize that it's theorem 2.1 at all, but you should make a note, is that differentiability, so if it's differentiable, then the function is continuous. So if the function is differentiable, then the function is continuous. Now, just because the function is continuous does not mean it's differentiable. It's not an if and only if, which we talked briefly about, I think back like in geometry in your logic days. So if differentiable, then continuous, but you can't say if continuous, then differentiable. Such as can be seen by what we stated here with the sharp corner, or maybe with the vertical tangent right here, where the slope doesn't exist because it's vertical. So, however, if your function is differentiable, then you know it is continuous.
Slope.
Yeah, no, it's continuous. Good job. Good job. Good job.
I said derivative.
Good job, bud. Does it bother you if people call you bud?
Oh.
Oh, nice job, bud.
Is that my proper title?
You know who
Lord
gets that?
over.
Like very
Some guys on the fire crew.
well, that too.
That's where I was like thinking about it. Nice job, bud, or buddy. Hey, good job, buddy.
Asher Howie.
Oh,
Don't call her bud.
I don't know right now. That's great. Okay. Okay, so you guys have to do your numbers 1 and 2. On 1 and 2, they give you a graph, and they just want you to estimate the slope simply by finding the slope of the blue line by counting. So you'll see on numbers 1 and 2 in your book that you'll just look at the blue line slope and then give the slope of that. So you're just estimating the slope that way. Then we're going to go to, let's do some actual problems where it says find the slope of the tangent line to the graph of the function at the given point. Now, when we do this, you will need to use our limit definition. And let me erase this. Maybe we're going to come back to that, but we'll keep our limit definition using limits. I mean, our derivative definition using limits. However, if I said, okay, so find the slope at the given point for the function, add the function part, and we'll just call this number 1. So if I give you, hey, you have f of x is equal to 3x minus 5 at the point 4, 7. So at the point 4, 7 for this function, what is the slope? Now, if I said use the definition of the derivative using limits, okay, you have to do that. If I didn't say that, I said, okay, we're going to toss out calculus for a minute and just say, hey, what's the slope?
We already give you 3.
Yeah, good.
Good job.
So if it states this, okay, just it's 3. Very good. Now, what I'll state, and that's fine, we're going to leave it there. What I'm going to state on the test is, the mid-chapter assessment, use the limit definition for derivatives to find the slope. Now, with this one, we could do that. But what if we were given something different, such as, let's say we have this, f of x is equal to x squared minus 5. And then I said at the point 3, 4. So We actually don't really worry about the 4 part in the sense of like, it's occurring at 3 comma 4, but it's, I mean, we do end up worrying about the 4 part, but we could just say at x equals 3 is fine, which then you could find the 4 from that. So what we have is, we have a parabola, right, x squared minus 5. What's the general look of the parabola? You know, it opens up,
It's to the,
down 5, right?
oh,
Yeah, so it'll be down 5 like this.
how does it, when does it shift right?
If it goes like this, something like this, let's say, if the
Then it would go to the.
function, if the value is attached to the x and that's also getting squared. Yeah, then it would shift to the right too, and then down 5. So we know the general look of this, over 3, up 4. We'll call that 3, up 4, and then we want to find the slope at that point right there. Okay? So there's your general look of the parabola. You want to find the slope of that. So what are you going to guess the slope is? Positive or negative for starters? Positive. Excuse me. Are we going to guess the slope is like a casual 1/4? Rise of 1, run of 4? No. But we don't know, is it going to be, you know, is it going to be, now my picture shows it's going to be really steep, but we don't know if it's going to be steep. But we would guess is that it's not going to be like a fraction necessarily. Because if you have a slope, like instead of 1/4, it's going to be a rise of 1 and run of 4, you know, and the graph would be really stretched out like that. So probably, or the tangent line would be such. So it's probably going to be not a fraction, but it's not necessary. This makes it look like it's a rise of 5, a run of 1. You know, so your slope would be 5, possibly like up 5, run of 1. But it's just a sketch, so we can't quite say that. But we do know the slope is going to be at least this. We know the slope is going to be positive. The sketch can mess things up. So what we're going to do is we're just going to do our definition of the derivative right here. We're going to say what is the slope of, right here, using the limit definition, f prime of 3 is equal to, okay, the limit as delta x approaches 0, and then of, okay, f of 3 plus delta x minus f of 3 all over, and then you could state 3 plus delta x minus 3 just to see the x2 minus x1, but we know that we should end up with just delta x in the bottom always. Okay? So even though they don't put that here, I showed it here, I didn't show it there, I didn't show it here, that is what's happening is you're taking your x2 and then your x1, and then you'll always just be left with that change in x. So really what you're stating is, here is your point, and then there's another point up here. So this point we know is 3, 4. This point is 3 plus delta x, comma, f of 3 plus delta x. Squeeze that in there. So that's f of. So we already know that the f of 3 is 4, and we could double check that, right? 3 squared is 9, 9 minus 5 is 4. So 3 plus delta x, this is what you'd have to show, is that this is like f of chicken, right? It just goes right in, or we're doing this one, right? It's just going in here. So in other words, you have 3 plus delta x squared minus 5 minus f of 3, which was just 4, which, you know, maybe we should show that just so we could see that we're plugging it into the function. 3 squared minus 5. All over, and then you'll just put delta x, and I need to actually include that the limit as delta x approaches 0. Now with this, we need to FOIL this out, because you can't take the limit as is, because delta x can't go to 0. But what should happen is, you should be able to, in the end, cancel out the delta x's. Should all cancel out for us. So all I've done there is I foiled 3 plus delta x, and that comes out to be 9 plus 6 delta x plus delta x squared. This is where in pre-calc, when they use the variable h, it's a little bit easier because then it's just 6h plus h squared, and then you don't have the delta x cumbersome notation, but we'll stick with delta x. If on the test you change this to h going to 0 and then just call this h and h, that's no problem. You can do that. Not an issue. So then our 9s are going to cancel, right? And then our 5s are going to cancel. And then what we're left with is, I'll show the step, but 6 delta x plus delta x squared all over delta x. This is, again, the limit as delta x approaches 0. And then our delta x's are going to cancel, right? And then you're left with just 6 plus delta x, which again, I'll show the step. The limit as delta x approaches 0 of 6 plus delta x. And then you plug in 0, and you're just left with a slope of 6, which, if we backtrack, I stated the slope, here was steep. I said, but it may not be 5, but actually I was correct. It was close. It was a slope of 6, so my picture was actually accurate. So that's fine. The slope actually was 6, meaning it's pretty steep right there. It's a rise of 6 and run of 1. So I was accurate in my drawing. I was just thinking that 1, 2, 3, I guess whatever. So the drawing was somewhat accurate. So you have a slope of 6. Now that's not the general slope, that is the specific slope at 3. So then if you said, well, what's the slope at 5? Then you would need to do this process over again at 5. Okay, and it's getting steeper. Now the other thing though you could do is, if for whatever reason, like they will say, find the derivative of the function by the limit process. This said find the derivative, or find the slope, at the specific point. So that's why we said f prime of 3, because it was at 3, we wanted to know what is the specific slope. But if they said just find the derivative is going to be actually, of f of x, we'll do the same one, x squared minus 5. The derivative is just going to be the general slope formula for the entire function. And so here, this slope is always 3, right? That's why the slope is 3. It's constant. Here, this slope was 6, but that was only 6 at the specific point. So when we end up finding a derivative of a function like this, the derivative, f prime, whatever it is, which I know what it is, and you guys probably remember what it is, possibly by using the cheater method, this will have something with an x involved, meaning you're going to, whatever you plug in, like f prime of 3, f prime of 2, your slope will be changing, so it has to have a variable involved to allow for a giant change. Yeah, it's going to be 2x ultimately. Yeah, if you remember from last year, you drop the exponent, reduce it by 1.
So.
But on the, go ahead.
The derivative of x equals 5, or the derivative of 5 when it's 5 is 10. For that equation.
For the which equation? This one?
The same one we were using, so like how you were like, if you were to be 5, it'd be c.
Oh, at 5. Yeah. The derivative at x equals 5 would be 10. Yep.
Okay.
So on the test though, and like what you're going to practice is, just because that's where it all originates before using the cheater method of drop the 2, the power rule, and then reduce by 1, and the derivative of a constant is 0. We work with the limits. So you say, okay, the general derivative then is going to be the limit as, so f prime of x equals delta x approaching 0 of f of x plus delta x minus f of x all over And I think we've talked about it enough. I'm just going to write delta x in the bottom. Because we know it's x plus delta x minus x. Here's delta x. Now, you say, okay, what am I supposed to do with this? Well, you're going to take this and you're going to plug it into your function. Okay, so you're going to say the limit as delta x approaches 0 of x plus delta x squared minus 5 minus whatever f of x is. Well, f of x is just your original function, x squared minus 5, all over delta x. So you're just taking x plus delta x and you're plugging it into this function. That's where we get the x plus delta x squared minus the 5. That's where that comes from. And then when we FOIL it out, it's going to be x squared plus 2x delta x plus delta x squared minus x squared plus the 5 all over the delta x. And then we should be able to, let's do it all in one fell swoop. X squareds cancel. 5s. Wait a second, what happened to my 5? Oh, I forgot my 5 there. Oh, my bad. Minus the 5, that minus 5 goes there. Minus the x squared plus the 5. So the 5s cancel, the x squareds cancel. And then you have 2x delta x squared, right? So delta x cancels with that one, cancels with that one. And I'm left with 2x plus delta x. But it's the limit as delta x goes to 0. Therefore, this is 2x. Which, what do we guess it was? 2x.
Fun.
So work on that limit process a little bit. Ultimately, we go away from it and do the power rules and stuff. But just initially, and you will have to show this process on the mid-chapter assessment and the test for at least one problem there. And then we jump into the power rule in 2.2 and start using that and all the other rules that we learned. Okay? Questions, comments, concerns? Do you have a test next period?
What? No, I just don't want to overtake.
Oh, nice. Okay, so make sure